Hello everyone, in this video we're going to be looking at section 10.5, which is area and arc length and polar coordinates. So you already know how to do area and arc length in rectangular coordinate system, right? Area was just the integral of the top minus bottom, and arc length was the square root of 1 plus the derivative squared. So now we're going to look at what that is in this polar coordinate system. So we just start out for what a theorem for what that is. And it says if f is continuous and non-negative, right? So that's important. Continuous and non-negative on the interval from alpha to beta, and beta minus alpha is between 0 and 2 pi, then the area of the region bounded by the graph of r equals f of theta between the radial lines theta equals alpha and theta equals beta is given by a equals 1/2 the integral from alpha to beta of f of theta squared, or 1/2 the integral from alpha to beta of r squared d theta. So remember, what do these radial lines mean? Remember, a radial line is just going to be, if it's theta equals alpha or theta equals beta, that just means go to this is my coordinate system, go to the angle that's theta and then draw a line there, right? So that's what we're talking about here. Okay, so where does this formula come from, right? Right now it kind of seems like magic, but it actually comes from the area of a sector of a circle formula. So for example here, if I had this point here and I had this sector of a circle, right, say this angle is theta, and I wanted to find the area of this, and this is radius r, and I wanted to find this area, right here. Well, how would I do that? The area of that sector would be 1/2 times theta times the radius squared. Notice that's starting to look something like our formula for our area, because the idea is going to be very similar to the idea of using the integral. So before, when I looked at the area underneath the graph, I said, okay, I've got a bunch of little rectangle, and this is in the rectangular coordinate system. I got a bunch of little rectangles. I'm going to take infinitely many of those rectangles, and that'll give me the area underneath the graph, right? Adding up the area of all of those rectangles. Well, the same idea is going to happen here, except with sectors of a circle. So say this is my graph. Make it a little bit bigger. And say this is my graph, which is f of theta, right? R equals f of theta. And then I have these radial points, right? These happen at, let's say we're trying to find the area. Say this is theta equals beta and theta equals 2 alpha, right? So this right here is alpha, and then this angle here is beta. Okay, so I'm trying to find the area that is bounded by these guys. So say I want to find that total area. Well, what I can do to find this total area is I can say, well, I can think about having like a bunch of little sectors like this. Right? If I put a bunch of these little sectors in there that look like this guy right here, then this would be like a delta theta, because my angle is changing a little bit. This would be like a delta theta. This would be like a delta theta, and this would be like a delta theta. And I could add up all of those sectors, right? But as delta theta gets really small, as I add up infinitely many of those sectors, then I will get adding up infinitely many, making delta theta get small. That's that whole idea of the integral, right? So the total area is going to be the sum of infinitely many sectors, right? And that's the idea of an integral, right? Because the area of each one of those sectors, right, is just going to be, if this is like theta 1 and theta 2, it would be 1/2, and then it would be the theta 1 squared, or I'm sorry, theta 1 r squared And then I do that for each different one. So I get all those thetas, all those radiuses squared. The radius is going to be the same every time. And then if I add up infinitely many of those, I get this formula that we're looking at right here. All right, so that's kind of the idea. I didn't want to go too far into detail of it, but it's just the same idea that we've used over and over again, where we're adding up infinitely many things, which is the idea of an integral. Okay, so now we need to do an example. So find the area of one petal of the rose curve, r equals 3 cosine of 3 theta. So anytime a radial function has this form, it's always going to be a type of rose curve, right? It's called a rose curve because it's got petals to it, right? So the first thing we need to figure out in this example is, right, in order to use our formula for what the area is to figure out what alpha and beta are, right? And alpha and beta, we should be very specific here. We're doing this d theta, right? So what theta is an angle, and so alpha and beta are angles, right? Alpha and beta are angles. So we need to find angles to plug in there, right? So notice that in this example here, how are we going to do that? Find the angles, which are alpha and beta. Well, we notice that to close the rose petal, right? So to close the rose petal, if I do one little loop, which is we're trying to find the area of that one little loop, to close it, the graph crosses the pole or the origin, and at the pole or the origin, that radius is 0, right? At that point, remember, we can represent the pole as 0 and any theta we want, right? Any possible angle, but the radius is 0 there, right? So we know that the radius is 0 when I cross, which is going to be like when I start and finish this rose curve, right? So my beginning and end, or my alpha and beta, are going to happen when my radius is 0, right? But notice what is my function is a function of r, right? So when I say, okay, I know the radius is equal to 0, well, what is the radius? The radius given by the equation is 3 cosine of 3 theta, and that equals to 0. So when this radius equals to 0, that's going to give us our values, our starting and ending values for my angle, or my alpha and beta. Right? So solving this, I end up getting cosine of 3 theta equals to 0 if I divide by 3. And then I end up getting 3 theta equals to cosine inverse of 0, right? If I solve for theta. Well, where is cosine equal to 0? Cosine is equal to 0 at pi over 2 and negative pi over 2. Right? So I end up getting, right, this I end up getting pi over 2 and negative pi over 2. Those are the 2 points that give me cosine inverse equal to 0. So I say, okay, 3 theta is equal to pi over 2, and, or it doesn't really matter what you say, and I get 3 theta is equal to negative pi over 2 to solve for theta. And then when I solve for theta, I divide by 3, and I end up getting theta equals pi over 6, and theta equals negative pi over 6, right? And if you look at this, picture, right, this dotted line right there, that is the line theta equals pi over 6, right? Because it's the line at the angle pi over 6. So let's draw it a different color. So this guy, let's draw an orange. This is the line theta equals pi over 6, just like we have lines y equals 7 is the horizontal line at the y value 7, and x equals 3 is the vertical line at the x value 3. Same thing here. And then this guy right here is going to be the line theta equals to negative pi over 6. All right, so what does that mean? My starting value, my smaller theta, is going to be my beta, or I'm sorry, my alpha, where I start, right? So pi over 6 is my alpha for that formula, and, sorry, negative pi over 6 is my alpha for that formula, and pi over 6 is my beta, right? And I know what my radius is, so I can just roll ahead with my area formula. right? So my area formula says A is equal to 1/2 the integral from alpha to beta of the radius squared d theta. So plugging our values in, we end up getting 1/2 the integral from negative pi over 6 to pi over 6 of the radius, which is the radius is what's given by the problem. It's just the radius function, which is 3 cosine of 3 theta, and we're going to square that, d theta. Okay, so in order to square that, it's just squaring a binomial. So we do the first one squared, 2 times the first times the second one times, or actually, no, sorry, that's not a binomial squared. That's just something squared. So I square the first term and the second term. So 9 cosine squared of 3 theta d theta. And now what I'm going to do, I've got cosine squared, right? And I'm not really familiar with how to integrate cosine squared if I don't have a sine factor outside. But what I can use is the power reduction formula. And in this section, we're going to use it a lot. So the power reducing formula. And what is the power reducing formula for cosine squared? It says that cosine squared of u is equal to 1 minus 2, or actually no, plus 2 cosine of 2u over 2. Oops, sorry, this should just be cosine. Which is the same, the way I like to use it, it is 1/2 plus 1/2 cosine of 2u, right? So this is typically the one that I like to use here. So I'm just going to cut this one out and keep this one. All right, and that's what we're going to use to fix this part. So that way, and why is this helpful? Why is the power reduction helpful? Because now this is regular old cosine that I can integrate, and this is a constant which I can also integrate. All right, so I get 9/2 if I pull that out to the front, times the integral of negative pi over 6 times to pi over 6, and then I have 1/2. But now I got to be careful of how I do my argument, right? So this is, it says take whatever was being squared on the inside, or whatever's on the inside of the square function, and multiply it by 2, right? So this is 1/2 plus 1/2 cosine. Instead of 3 theta, it's going to be 6 theta, because I multiply it by 2, d theta. So now I can integrate. So I get 9/2 times, I get 1/2 theta, and then the antiderivative of cosine is positive sine, so I get plus, and then I get the 1/6 because I'm taking the antiderivative, so I divide by 6. So I end up getting plus 1/12 sine of 6 theta. And I'm going to evaluate that from negative pi over 6 to pi over 6. So if I do that, I end up getting 9/2 and then 1/2 times pi over 6 plus 1/12 sine of 6's cancel out, so sine at pi, minus 1/2 negative pi over 6 plus 1/12, and then it's sine of negative pi. Well, conveniently, sine at pi and sine at negative pi are 0. So I end up getting 9/2, and then this is pi over 12, and then 2 minuses make a plus, so plus pi over 12. So I end up getting 9/2 times, if I add those up, they have the common denominators. This is 2 pi over 12. So 2's cancel out. This is 3, this is 4. So I end up getting 3 pi over 4 as my area of that first rose petal. Okay, so now let's look at another one here. So this one says find the area of the region lying between the inner and outer loops of r equals 1 minus 2 sine theta. And this is called, I'm not really sure how to pronounce it, but it's called it's Lima, and then it's got a C with like a little squiggly underneath it. O-N, so I call it a limacon. I don't know how to pronounce that, so I apologize if I'm butchering that. But that is a polar shape that happens a lot, and it's when we have that kind of center that's hollow there. Okay, so same thing as before. In order to find the area, we need to find the theta where you start and finish, right? So we need to find the angles alpha and beta. And again, where we have this loop, right, that's where we're trying to find the area of when we start and finish. So when we have this loop, that closes the loop by crossing the pole or the origin, which again happens when r equals to 0. So same thing as before here. I have, this is what r is, and I have that equal to 0, right? So I get, when I start to say that I get r equals 0, well, what is r? R is 1 minus 2 sine of theta, and I'm setting that equal to 0, and I'm solving for theta. So if I do this, I end up getting sine of theta equals 1/2, which means when is sine of theta equal to 1/2? Well, that happens at pi over 6, and that happens at 5 pi over 6, because remember, sine is y values, and so that's where that happens at the unit circle. So that's where I start and finish, right? And so the fact that I don't have to do anything special for this hole, because that hole is accounted for because of the shape of r, right? So as long as I just say, hey, I'm starting at the correct theta, which we found to be pi over 6, and I'm ending at the other correct theta, right? Because this is starting it, and then it goes all the way. It starts, try that again. It starts like this, and it starts here at pi over 6, and then it goes all the way there and through there, right? So I end up getting what I want here. Okay, so area is equal to 1/2 alpha beta r squared d theta. So in our case, I end up getting 1/2 the integral from pi over 6 to 5 pi over 6, and then r, which is 1 minus 2 sine theta squared d theta. So this is one where I am going to need I am going to need to square this, what I was trying to do in the previous example, right? So pi over 6, 5 pi over 6. So this one's going to be 1 minus 4 sine theta plus 4 cosine squared theta d theta. Once again, I'm going to use the power reduction formula, right? So I'll draw it in blue here. I don't want to write it again, or sorry, in green. I don't want to write it again, but it's this power reduction formula that I've written right here. So I end up getting 1/2 the integral from pi over 6 to 5 pi over 6 of 1 minus 4 sine theta plus 4, and then it ends up being 1/2 plus 1/2. The only thing I need to be careful of here is what do I do to my arguments? In this case, the cosine was just regular theta, and then I multiply it times 2 to get what's inside the cosine regular argument. Right, so in this case, this is going to be cosine of 2 theta, since what I was squaring was just regular theta. And then this is all going to be integrated. So 1/2 the integral from pi over 6 to 5 pi over 6. I have 1, and then this one would be 2, so 1 plus 2, so I get 3 minus 4 sine theta, and then plus 2 cosine of 2 theta d theta. Yep. And then we integrate, so 1/2, we get 3 theta. The antiderivative of sine is negative cosine, so this ends up being plus 4 cosine of theta. And then this ends up being positive because the antiderivative of cosine is positive sine. And then I would take 2, but then I would divide by 2 because of that 2 on the inside. So this ends up being just cosine of 2 theta, and evaluate that for pi over 6 to 5 pi over 6. And if I do that, I won't bore you with the details, but I end up getting 1/2 times 2 pi minus 3 radical 3, which gives me a final answer of pi minus 3 radical 3 over top of 2. So that is my area for that limacon, or this pink part. Right? Again, I didn't have to worry about the inside circle because that's a part of the shape as long as I had the right theta or alpha and beta. All right, I'll go ahead and end this video here. Thank you.